Now let's do an example where we're going to find the rate expression for this reaction. So we can write the rate in general as the rate constant times the concentration of the reactants raised to some power. And we're going to find what A and B are from this experimental data. We have 3 sets of data, and you can see in experiment 1 and 2, the concentration of A changes, but the concentration of B stays the same. And then between experiments 1 and 3, the concentration of A stays the same, but the concentration of B changes. So we use 1 and 2 and 1 and 3 to determine what little a and little b are. So let's see how we do this. So this is the rate for experiment 2 divided by the rate for experiment 1. And you'll notice that the concentration of B doesn't change between experiment 2 and 1. So the concentration of B will cancel. And the rate constant cancels. And so we'll just have R2 over R1 is equal to concentration of A for experiment 2 divided by that for experiment 1 to the little a power. Now we'll take the log of both sides of the equation and solve for A like we did before. Okay, so now we can determine what A is, and we plug in numbers. So I'll have the log of the rate for experiment 2, 2.4 times 10 to the minus 3 molar per second, and divided by the rate for experiment 1, 4.2 times 10 to the minus 4. And then divide that by the log of the ratio of the concentrations. So the concentration for experiment 2 for A is 0.64 molar, and for experiment 1 it's 0.27. And I'll round to a whole number because these, for our class, we're assuming little a and b are whole numbers. So we found that little a is equal to 2. So now we have our exponent a, and that's 2. Let's find the exponent b. So we use the same procedure. And this time we'll use experiments 1 and 3 because a doesn't change but b does. Okay, so rate constant cancels and the concentration of A cancels because it is the same in experiment 3 and experiment 1. So we just have this ratio. So we can take the log of both sides of the equation and solve for B. And putting numbers in, so we'll have the log of the rate at 3 and 1. So that's 1.2 times 10 to the minus 3 molar per second divided by 4.2 times 10 to the minus 4th. And I'm not writing the units because the units cancel in this quotient. And then divide by the concentration of B. So in experiment 3, it's 0.3 molar. And again, the units cancel. And experiment 1 is 0.18. And then rounding to a whole number, I get 2 for B. So now I know my rate expression. My rate expression is equal to So I found the form of the rate expression for this particular reaction through my experiments. Now the last thing I can determine is the value of the rate constant K. And I can just pick one of these experiments or all three and get an average. But I'll just pick one of these experiments and solve for the concentration, solve for the value of K. So solving for K, K is equal to rate over concentration of A squared divided by B squared. So I'll just pick one of these. I'll just pick experiment number 1. So I have the rate. Now my units aren't going to cancel, so I'll write my units. And then the concentration of A squared, 0.27 molar squared, and the concentration of B squared, 0.18 molar squared. So this is my value for K. So I get 0.18, and my units, you can see, are going to be, so going to have molar cubed in the bottom. So I have per molar cubed per second. So this is the value of my rate constant.